Thank you, Professor.
Professor Miasbah, Sandra.
Okay, let me give me a second. I'm giving permission to everybody. Hold on a second. I have to do that individually. Let me have everybody first. Let's see. Who doesn't have permission? I guess I have given permission to everybody to record. If somebody is missing, let me know so I can add them up. At this moment, I do not see Lily Park and Jonathan. These are the only two that they are absent at this moment. Let me put this aside.
Professor, can I get permission to record? This is Alex.
Correct. Anyone else?
Thank you.
I guess I gave permission. I have to go one by one, so I may miss a person. So let me know if anybody is missed. Jonathan is in. Permission. All right. It seems everything is set, and I have almost everybody except Lily Park. Hopefully she's fine and will join us soon. We have 30 people present, and it should be 31. Okay. First of all, I would like to remind you that the midterm exam 2, the last day extended due time by the end of today. So if whatever you've done, put it there. If you want to make any correction, still you can make a correction before the end of today, even if it's been graded. You make the correction, I can readjust the grade, and that would be taking care of that. I am going to post the final exam. You will find it in Canvas. Soon you will have permission to look at it. We can start working on it. It's related to this chapter. This is the part 1 of exam, and I will have another one from the next chapter we study, and that would constitute your final exam. So you have time to work on it. Don't jump into the solution last day. It won't be sufficient to work just in one day. You can ask questions. I can guide you through these problems if you need to during the office hour or at the end of the class or anytime that is proper. I do not mind to answer your questions, but at the end of the day, you have to prepare the paper of all these solutions to the best of your capability. I have, for the midterm exam, I have some of the papers fairly extensively written, nicely put together, with everything being asked correctly addressed. And I have some papers that, to me, it doesn't show still you have basic understanding of not only theory of elasticity, but probably going back to mechanics of material, and that is what is up to me. So please do work on this, prepare them as far as you can, and then we start the exam for the final, which governs this chapter that we went through, and also the next one that comes. We are going to complete this chapter this week, today actually, and next week we have a class on Tuesday, then we have Thanksgiving, so it's time to enjoy your time a little bit over there and catch up with the material that you fall behind and you want to work on it. And then following that, we have a week or so that we work, and that's it. And if you have prepared all this paperwork during the final exam time, you don't need to worry, and you can work on other subjects of your interest. So start working on these problems as soon as they are available to you. I strongly advise you that you work on them independently on your own, and it would be very worrisome to me if I see a mistake that somebody did, for example, writing 3 times 4 equal to 13, and another person copies that and says 13. It means that those are copied from one another. Otherwise, the chance of doing the same multiplication mistakenly the same way, it doesn't make sense. So work on them independently, and I am relying and trusting you guys. And again, the presentation of all the lecture notes and all the exams and all the effort that we do here is to build up the strong knowledge in you guys, so you will be confident engineers as you move on. And if you want to do further research work, you have a very strong basis to do so. And it doesn't make sense, as I mentioned to other students, to sign up to swimming class and pay for that, spend your time most of all, and instead of learning swimming, you just play around, don't do anything useful. At the end of the day, once you are exposed to water, you can get drowned. And that would be exactly the same thing if you do not learn the subject and it comes to you, you would regret why at the time that I could study, I didn't. So it's for your benefit. Don't think that it is, you are doing it for me. You're working on these problems for your sake. All right, what we learned in this chapter is that we can express stress and stress functions and displacement and boundary condition, everything in terms of a composite, in terms of a complex number. We have shown you guys that if a proper complex function is chosen, such as it has a derivative, differentiable complex function is chosen of any form, there are millions of possibilities, then the real and imaginary part of that would be proper solution to the stress function. And from there, we calculated the stresses, calculated the displacement. So the work would be fairly straightforward. Now, how to choose those complex functions for a specific problem that you have? It, of course, should match the boundary condition you know, every of these complex function would be the solution of the problem, but which one solution of your own problem of interest? The final result should match the boundary condition of your interest. And there are mathematical methods. If you go through the whole things here, it involves a lot of math. And I don't want to bother you guys with details math of this or that specific problem. All we are trying to do is build up the foundation so that you can work on any specific problem on your own. So the next step is to introduce the concept of a curvilinear coordinate system. And in the probably this page that I picked it up in internet, it has a nice picture here. If you're working on Cartesian coordinate system, the picture, the black picture in the bottom to the left, it shows the position of any point in the space can be defined by the coordinates of that point on a sort of a Cartesian coordinate system. And lines drawn horizontally would mean constant y, and lines drawn vertically, it means constant x. So constant x and constant y would be these straight lines, and you're breaking the space into these squares. Now, this space can be identified as real axis and imaginary axis. So anything on x-axis would be real, anything on y-axis would be imaginary, and a point such as A here would have a real and imaginary component. Now, whatever A is, it could be defining the stress in that location, it could be defining the displacement, it could be defining anything of your interest, but we can map that location into a space which is, instead of this straight line, has this curved line. One is being psi and one is being eta. And in fact, you are mapping the pictures here into that other space. The square that you have here becomes this curved space. If I define this Cartesian coordinates in terms of the variable z, which has real and imaginary value, x plus iy, where x is the x coordinate and y coordinate of the point here, and it is shown as a complex variable. Now, if I define a complex function, any complex function, such as zeta of z, where zeta is a differentiable analytic function, then if I know x and y, then I know I can convert that to the z function, and the z function would have the real value psi and the imaginary value eta I. And psi and eta would be the coordinates of any point here in the other space, in the mapped space in the other shape. So all we say, we transfer everything which is given in terms of z through this function of zeta into psi and eta. So for every value of x and y, there will be one value of psi and eta defined. based on that zeta function. This zeta function is our mapping function. Now we can make advantage of this concept for the curvilinear motion and solve problems of different form. For example, if I have a geometry which is an ellipse or a plate, a large plate, infinitely large plate with an elliptical hole, I can use the curvilinear coordinate system, such as ellipses cofocal. That means they have the same foci. Ellipses such as this one would be my psi variable, and normal to those which are hyperbola of a different form would be my eta function. So it's just similar to that. Straight lines becomes hyperbola, vertical straight line becomes hyperbola, and the horizontal one becomes these ellipses. And at any point, the intercept of these two lines would be coordinate in the new coordinate system. And we have also shown you that if the conversion, if the mapping is done by this zeta function, any function of z, for example, cosine hyperbolic of z, for example, tangent of z, for example, logarithm of z, or z times logarithm of z, or any function of combination of z that you can assume, then get the real and imaginary part of this function into the psi and eta, which are the coordinates in this new coordinate system. Some people probably lost the internet. All right. So the aim is that create a curvilinear function such as one of my coordinates, such as psi, would be a function of ellipse, which would define an ellipse. And the one that we found is this function. X, Y is being now mapped into psi and eta, where, as we have shown, the constant psi, it is the equation of an ellipse, and constant eta would be the equation of a hyperbola. Christopher is coming back. All right. So that mapping function that we talked about to go from a Cartesian coordinate system into the elliptical curvilinear coordinate system is this function. Our zeta function is, in fact, cosine hyperbolic of zeta is equal to z. Or the inverse of it, zeta would be arc cosine of z. So if x and y is given, z is defined, arc cosine of that can be calculated. And once you calculate that, get the real and imaginary part of that, it would be real and imaginary part of zeta, and that would be the coordinates in elliptical coordinate system. That is math behind it. There isn't that much more here. Now, in this case, we went through certain math here the other day and proved that if that zeta function is chosen, a complex analytic complex function is chosen, we are assured that the coordinate system in the map space will be perpendicular to each other, like x, y, which are mutually perpendicular to each other. Now this elliptical paths, elliptical coordinates, and the hyperbolic coordinates, such as psi and eta, would be perpendicular to each other. So we begin introducing the mapping as we have indicated, such that z will be mapped into zeta by this function, simple cosine hyperbolic zeta. And if we expand that, the real and imaginary part of that would be cosine sine hyperbolic psi times cosine eta plus I sine hyperbolic psi plus sine eta. Derivative of that zeta, f prime zeta, would be sine hyperbolic of zeta, and it would be given by this function. And it can be defined in a polar coordinate system, where j is the radial distance and alpha is the angle, according to this equation. So j cosine alpha is equal to c sine psi times cosine eta, and j sine alpha, there should be alpha here missing, is equal to c sine psi times sine eta. And you can see that from the angles that they make with respect to each other, without going into the detail of it, would be perpendicular to each other, as we expect. Now, suppose we have chosen this curvilinear system of the mapping system, where the Cartesian coordinate system is mapped into psi and eta. We can directly calculate stresses in this new coordinate system. The angle that they make with respect to each other, the angle that psi makes with respect to x-axis, is shown with alpha, and the task is only simple transformation by rotating the coordinate system in the direction such that it makes an angle alpha with respect to psi. And work it through. And as we have shown here in this picture, we have two equations. Sigma x plus sigma y is equal to sigma psi plus sigma eta. The other one should be eta. I already wrote these things, so there's some mistake here. Sigma eta plus minus sigma psi plus 2 dot psi eta is equal to sigma x minus sigma y, and so on. Where you can see in this equation, the angle alpha is obtained by getting the derivative of the mapping functions f prime. It is the same angle. So alpha will be obtained by getting the derivative of the f prime z over the conjugate of that derivative. It gives you e into power 2 alpha I, and from that you can calculate that. And similarly, displacement will be given in the curvilinear motion, curvilinear coordinate system. So these are the final equation that we can use with any curvilinear coordinate system. I'm not going to go over detail of simple algebra to show these equations. It's shown in the couple of previous slides, but this is what we need to consider to work through any problem of curvilinear motion, curvilinear coordinate system. Suppose the state of the stress in the Cartesian coordinate system is given, and state of the displacement u and v in Cartesian system is given. We define a zeta function, a mapping function, a complex function of z. And then from there, we want to see in the new coordinate system, curvilinear coordinate system, where one side is zeta, one side is psi. What are the effective stresses? These are the equations that defines the stresses. The above equations that you see, these three equations on the top, we have seen it before when we were talking about the complex function, the stress and displacement in Cartesian coordinate system is given by these three equations on the top. A similar equation are derived on for the curvilinear coordinate system. This is Cartesian, the one in the bottom is curvilinear. We can see similarity between these equations. To work through this equation, of course, sigma x, sigma y previously is calculated. So you put it here, and u and v is calculated, so you can get anything. The only thing you need is this part, e into power 2 alpha I. You need that one to calculate alpha, actually. And as we mentioned, this term is equal to zeta, the mapping function, derivative of the mapping function over the derivative conjugate of the derivative of mapping function. And all of that can be calculated. For example, assume our mapping function for the elliptical coordinate system was c times cosine hyperbolic of zeta. So from this, we can calculate derivative of zeta and conjugate of that, get the ratio. From there, we get the expression here, and angle alpha. What's angle alpha? And this is calculated. You can put it here. Sigma x, sigma y is already calculated in Cartesian coordinate system. So you should be able to calculate component of the stress in curvilinear coordinate system. If we do that and simplify, eventually the equations that comes here is epsilon, sigma epsilon plus sigma eta is given by this complex function. And the second equation gives the differences and it's given by this complex function. These complex functions calculated, you should be able to calculate sigma epsilon, sigma eta, and tau epsilon. And similarly, the equation in the bottom shows the displacement in the new coordinate system. So these are the equations that can be used to translate stresses from coordinates, Cartesian coordinate system into the curvilinear coordinate system. Now, I give you one just example here. There are many other examples in this chapter in your textbook. If you are interested, you can work through that. Here is the problem of infinitely large plate with an elliptical hole, which is under tension from all sides. So we have infinitely large plate with an elliptical hole. It's similar to the case we previously studied using polar coordinate system, but instead of elliptical hole, we had the circular. That's a problem of a similar nature. The coordinate system, the curvilinear coordinate system we use is elliptical coordinate system, which is defined by this mapping function. Z is equal to C cosine hyperbolic of zeta, where zeta, in XY coordinate system, Z function, the variable Z has the real value of X and imaginary values on Y-axis. Here in elliptical system, the similar coordinate, instead psi and eta are defined, and the plane here instead of Z would be zeta. So everything which is in Latin alphabet, X, Y, and Z, is translated into Greek alphabet. It's just like that somebody speaks English and writes it in Latin alphabet, and it is being now translated into Greek and using all the Greek alphabet. So Z equivalents would be zeta, X would be psi, and Y would be eta. The real and imaginary part of zeta are these two. And you can see the ratio of the derivative of f prime of z over the conjugate of that is defined by this. And from this, you can calculate alpha. Now consider an elliptical hole in the uniformly stressed plate, as I mentioned. If this is the hole, which defines the boundary of the hole here, this is the case that psi is constant. The variable psi is constant, that is equal to psi 0. So psi equal to psi 0 defines the ellipse of the hole, the boundary of the elliptical hole here. And you can see from the property of ellipse that the major and minor axes of that ellipse are actually C cosine hyperbolic of psi 0 and P would be sine hyperbolic psi 0. So the hole that we create, this is B, this is A, and A and B are related to psi 0 and C from these two equations. That is to say, if you know A and B, you can calculate C and you can calculate the value of psi 0. So then we can define the boundary of the hole. So once you define one of these ellipses, all the other ellipses are well defined. They are cofocal ellipses with the same foci, but a different value for psi 0. So as the psi 0 increases to a next level, you get the next ellipse and the next ellipse and so forth. We can see if psi 0 is a very small, that elliptical hole would collapse into a straight line, which would represent a crack in the middle of the plate. If psi 0 is very large, then we will get the problem of a circle. It degenerates into the circle. The variation along the ellipse from one point to the other is defined with the second coordinates, right? The eta coordinates, which are these hyperbola. And the values of these hyperbola could change from 0 to 2 pi. From 0, and you go around once, and you come back to where you were, and that's 2 pi. Do I make sense? All we need to do is to write the boundary condition on the surface of that ellipse. Shear stress is 0. Sigma x. I'm sorry. Okay, let me draw the picture here. We have infinitely large plate with an ellipse here. So at the boundary here of that plate, there is no shear. So shear stress is 0. And sigma x and sigma y both are equal to S. This is sigma y, and that is sigma x. So we have a rectangular plate that at infinity, there is no shear on its edges, and the stresses in both directions are the same, and it is sigma x equal to sigma y equal to S. The boundary condition here is defined in Cartesian coordinate system. But if you increase psi to infinity, because this is assumed an infinitely large plate, you come up to the same boundary of that plate. On the surface of the hole here, on the other hand, when psi is equal to psi 0, on that surface, I do not have the normal stress, and I do not have the shear stress. Stress is normal to that curve is equal to 0, and stresses, shear stresses will be also 0. We've shown that the relationship at any point on that plate, defining some of the stress in x plus y direction, will be given by this complex function. Therefore, at infinity, sigma x plus sigma y, which is equal to 2s, would be given by this function. When psi is equal to infinity. So when psi goes to infinity, this expression should be equal to S. That would be the boundary condition at the outside of that plate. From the second equation, we can write the boundary condition on the hole here. We have shown that on that surface, sigma would be S and S. I is 0, therefore we get the second equation. So that's one equation, that's the other equation at infinity. These are the boundary conditions. And we can write a similar equation on the boundary of the hole. And eventually consider psi equal to a sine hyperbolic theta. And then calculate the ratio, work through the math, and eventually, without going that much into the detail of the mathematics here, you should be able to calculate the components of the stress in eta and psi direction. And also the component of displacement. The maximum stress in eta direction, maximum stress in psi direction can be calculated. And what you get, one of the interesting solutions that you get here is that the maximum stress would be 2s times a over b. That is, if I have an elliptical hole, maximum stress at this point here on the ellipse would be 2 times s times a over b, where a is the major and b is the minor axis of the ellipse. A special case when a is equal to b would be that of the circle. For the case of circle, major and minor distances a and b would be equal to each other. Therefore, the ratio of a over b would be 1. So you can see the solution that we get is what we got for the plate with the circular hole. In prior chapters, when we were using the polar coordinate system, we derived the equation and we showed that the stress concentration factor for an infinite plate with the tension on both sides would be a factor of 2. That is to say, stresses increases twice as the value of S here. In the case of ellipse, it would be also proportional to that ratio. So you can see as A becomes smaller and smaller, that means the ellipse becomes narrower and narrower, going from a full circle to a wider ellipse, and then narrower ellipse, and then perhaps a line. You can see the ratio would increase, the stress concentration would increase by narrowing the ellipse by the ratio of A over B. So for a very narrow ellipse, we have a significant stress concentration. And in case when it goes to infinitely thin and it generates to a simple crack, a line, this formula shows that the stress, as we expect at this end, would be infinite, because A over B becomes infinity, B becomes very large as compared to A, and that ratio becomes infinity, then therefore it resembles a case of a crack front. And that equation is the basis of fracture mechanics when we are studying the effect of the crack, presence of the crack in the material. we can begin from this formulation. There was a lot of mathematics here involved, and I'm sure that I could have gone slower and go line by line and explain each line, but there isn't that much begin. It's just a simple mathematics. All we want you guys to realize, separate from details of math on each picture, again, is that we can generate a sort of curvilinear coordinate system. And suppose you want to study the case of a plate which is under tension, and it has a hole. It is not circle, it's not ellipse, which is given by a function of x and y. Equation of the hole in the plate is given. I can select a curvilinear coordinate system such that the boundary of that hole would be the psi coordinate of my curvilinear coordinate system. And normal to that would be my A. Since the coordinate system is chosen as such, psi equal to constant defines the location of that circle, and we can say easily stresses on that boundary, or we can define stresses on that boundary. We can say that, for example, the shear stresses is 0, the normal stresses is 0, only we have stress in one direction, and work through that and solve the problem. Now, this is as far as I wanted to go in this chapter. And I would like now to quickly expose you guys to the homework or the exam that would come with this chapter. It's like any other homework that we do, but I would grade you based on the, not only the effort, based on the correctness of your solution. Let me post it. And go over that. And you will see that later on your canvas. And if you wish, you can start working on it. Give me a second, I open the file. Starts from a very simple problem. To bring it here. This is the first, let me clear the annotation here. Let me make it larger. Determine the real function alpha x, y, and beta function of x and y that are real and imaginary part of the complex function that I showed you. So it's a real practice of your knowledge that how you can work with complex number and complex function. I have a complex function. One is z into power 2. One is z into power 3. The other one is tangent hyperbolic of z. Z is a complex number which has real and imaginary values. Now I am defining a function of z, which is, for example, equal to z squared. All you need to do in this problem, express z in terms of its component x and y, and then separate the imaginary and real part of the function of f of z. The real part would be alpha, and the imaginary part would be beta. Identify alpha and beta. In these simple cases, z squared, z cubed, and tangent hyperbolic of z. So tangent hyperbolic of x plus iy should be expressed as a function of x and y plus another function of x and y. This is real, that is imaginary. This is what I want to do with that problem. Very simple problem is the case of the first problem. I have identical problem in polar coordinate system. I would like to calculate the let me get this straight. I would like to calculate the real and imaginary part of some function as given here, z into power minus 2 and z logarithm of z, for which, let me get my pen. If z is given again as a function of the polar coordinates r and theta, you know that any complex function can be defined as r e into power I theta. So that's one form that we can express the complex number in polar coordinate system. So if z is defined as such and you substitute into this equation, expand it, it should be expressed as alpha plus beta I. Now, we want to find these two functions in polar coordinate system. Very similar to the previous problem, but in polar coordinate system. Let me see, where did I put the third problem? Now, if the z is a function of x and y as shown here, and our mapping function zeta has component psi plus eta I, it means mapping from Cartesian coordinate system xy into the curvilinear coordinate system with the coordinates of psi and eta. And if that zeta function is defined by this expression. Z is equal to I A cotangent hyperbolic of 1/2 of zeta. If this is the transformation or mapping function for us, I would like to go and calculate the component of x and y in terms of eta and psi. All you need to do is to substitute zeta psi plus eta I into that expression, expand it, separate the real from the imaginary part. The real part would be x, and the imaginary part would be y. And that's the task that you need to do. So these first three equations are simply a little bit work on our knowledge of complex functions. We bring the next problem. Which is a little bit more realistic problem. Concerning our theory of elasticity. Here we are dealing with a problem, a complex function of fourth and fifth order are defining my complex function psi and chi. Psi of z is a complex function of z into power 3, and chi is a complex function of z into power 4. And we know that the stress function would, as indicated in your textbook and also in our presentation, stress function can be given in terms of these two functions of z, psi and chi. Now, constants a and b and c in these expressions are real. So it is a plus ib and c plus id. These a, b, c, d are constants which are real numbers. We want, first of all, using that equation shown on the top, you calculate the stress function. Stress function should come as a function of x and y. So you substitute for chi or chi and for the psi into this expression and expand it, simplify it, get the real value, and that should be the phi function. Once you get the phi function, it should automatically satisfy the biharmonic equation of elasticity, compatibility equation that we discussed before. But I want you guys to show me that phi would indeed satisfy the elasticity equation, the biharmonic equation of elasticity. Then I am asking, is these two complex functions we chose analytic? That means they are differentiable. If so, it should satisfy Cauchy-Riemann equation. Check if these two equations expressed on the top would satisfy Cauchy-Riemann equations. Calculate the derivatives, first and second derivatives of this function, and use them into this expression in the bottom and calculate sigma x, sigma y, sigma z. So you should be able to define what is sigma x, sigma y, and tau xy in terms of the x and y. Then use the equation in the bottom that defines the displacement. And from there, you can calculate displacement u and v. Obviously, in the equation in the bottom, the real part of that complex function on the right would be u, and the imaginary part of it would be related to. Once again, I get the other. Open the other file. It's rather. That's the. Seems somehow. I had another problem that seems it's misplaced. I'm trying to find it out.
Professor, are you going to make the exam viewable tonight?
Yeah, I will give you the exam viewable probably by tomorrow. I have to sort it out. There is some. I have problem in different pages, so I have to put them together.
Okay, thank you.
Here we are. Okay. The next problem, as you can see here, is that if the stress function is given by equation shown here, I would like you guys to go and determine the boundary condition on a length of given segment and calculate the effective forces Fx NFY, as we explained the other day on, I guess, on Tuesday, and determine the effective forces and moment due to the presence of this function. That's it. These are the problems that we have considered for this chapter. And on Tuesday next week, we begin working a little bit on three-dimensional problems, mostly a more tangible problems that can be solved in three-dimensional problems. There are many problems that can be looked at. We have the bending problem, we have the torsional problem, we have the contact problem, many problems that can be studied in three-dimensional space. All we did up to now was two-dimensional cases. I would like to expose you guys a little bit onto three-dimensional analysis of theory of elasticity as well before we complete our course here. All right, I guess that this is all I wanted to say. I remain online if you have any question on the subjects that we discussed today, and also if you have any question on the previous chapters we studied, you're free to ask. We have 5-10 minutes, and we have an additional office hour, so I can stay as long as you want and answer any questions that you have. If you have no question, I'll see you next week on Tuesday. Otherwise, I am here to listen and you may ask questions.